I'm Norihiro Sugimoto from Keio University. Today, I would like to introduce our Venus general circulation model and its data assimilation system. So, as Professor Carne explained, the data assimilation is very widely used for the Earth's atmosphere to produce analysis data set and to obtain more accurate weather forecasts. Because of many observations and good numerical models. So analysis data set, which is continuous in time and space, is very useful to study atmospheric phenomena. So there are many analyses, for example, NCEP or ERA interim and JERA 55. For the Martian atmosphere, also there are several analysis data sets because in Mars, more observations are available compared to Venus, and there is good reproducibility of Martian GCM. So the Venus, it's a very interesting planet. The solid part of Venus is similar to that of Earth, but rotation period is very slow, about 243 days. However, the atmosphere rotates very rapidly, about 4 days. So this atmospheric rotation is called superrotation, and why such kind of superrotation developed is not revealed. So superrotation is one of the most important topics in the geophysical fluid dynamics and planetary atmosphere science, because we couldn't understand such kind of different dynamical regimes are developed compared to Earth and Mars. And also, we couldn't observe circulation below the cloud. For example, here, sorry, I couldn't point. Here, we have a cloud covered by whole planet, so we couldn't observe below the cloud. So the goal of this research to understand why such kind of superrotation is developed, we first produce analysis data set for the Venus atmosphere combined with Akatsuki Venus climate orbiter and our general circulation model, AFES-Venus. By combined with these two, we can produce an analysis data set which is continuous in time and space. So it's a first try. So Akatsuki Venus climate orbiter, which observed since 2015 December, we have many meteorological observations at multiple altitudes with different wavelengths camera, as shown here. Several altitudes we can observe. So this is an example of images. We have several altitudes by infrared and long wave infrared and ultraviolet images. Using these images, we can obtain horizontal wind and temperature, which are available to data assimilation. Also, we have developed atmospheric general circulation model for the Venus atmosphere, AFES-Venus, which is optimized for the Assimilation. In this model, we can solve three-dimensional primitive equation on sphere with hydrostatic balance. Using idealized solar heating and infrared radiation process, which is realistically but very simplified version of radiation process, and using also idealized initial condition of superrotation like this. Sorry. And assuming this kind of altitude profile of static stability, which is also realistic, we can reproduce many interesting phenomena on the Venus atmosphere. Here is the selected result of our AFES-Venus. For example, first, this is zonal flow in latitudinal distribution at different altitude. This one is AFES-Venus result, and also this is observations, which is a very good coincidence, these two. Also, here is the polar region. We have polar vortex with cold latitudinal band observed by Pioneer Venus orbiter, which is also reproduced in our AFES-Venus. Here we have Akatsuki IR2 images, infrared camera. There is streak structure in the Venus atmosphere, which is also reproduced in our AFES-Venus. So our AFES-Venus reproduced many interesting phenomena observed by Akatsuki and other orbiters. So it's a chance to try a data assimilation. So as Professor Carne explained, LETKF, we also use this data assimilation technique in our Venus GCM. So this scheme is already used for the Earth and Mars, and also a reanalysis dataset has been published. Because this technique, we can estimate variance by ensemble forecast, and it's easy to implement our AFES-Venus. So using this technique with initial state with some error, we can evaluate model errors by ensemble forecast. Then with observations, some kind of error, by LETKF, we can estimate most probable state with some error. This is another initial step to next ensemble forecast. By such kind of repeated process, we can produce analysis dataset in continuously time and space. So this is the setting of our data assimilation system. We use 31 ensemble members, and these are parameters of our data assimilation system. This is a schematic figure. If we have some observations like this, we can assimilate this by 4-dimensional LETKF, and we produce 6-hourly continuous dataset as an analysis. So previously, we have tested horizontal wind assimilation, which is driven by cloud tracking of ultraviolet images by Venus monitoring camera onboard the Venus Express launched by ESA. And this is an example of horizontal wind at 70 kilometer altitude. Here, zonal wind and meridional wind clearly suggests the signature of thermal tide, which is very important planetary scale wave. So assimilating these wind, we can improve temperature field like this, here without data assimilation and with data assimilation. The temperature field is very improved by such kind of phase shift, which is consistent with long wave infrared images, as shown here. However, this test, we couldn't produce analysis dataset because observations are about once a day, mostly covers southern hemisphere. So using Akatsuki continuous observations, we can create a more reliable analysis dataset. So in the present study, we assimilate horizontal wind derived by Akatsuki Venus Climate Orbiter. We again focus on the phase of thermal tide because this wave transport angular momentum upward or downward. So they contribute to maintain or produce superrotation. Also, we focus on superrotation itself. So here is the horizontal wind derived by cloud tracking of Akatsuki UVI ultraviolet images with this wavelength. Here is an example of zonal wind and meridional wind, which is assimilated at 70 kilometer altitude. And we have already produced 4 analysis datasets in those epochs. We focus on this epoch 4 because this epoch, we have many observations. Here is the time series and number of observations. And this line shows 4 observations per day. We have more than 4 observations per day, namely at least 1 observation every 6 hours, mostly. So this is a result of root mean square distance deviations from freedom forecast without data estimation. This is a time series of zonal wind and temperature in RMSD. These 2 months, we have many observations, and temperature is also improved by horizontal winds assimilation. So we focus in these 2 months because root mean square values are almost stable. So this is the horizontal winds in local time, longitude and latitude cross-section at 70 kilometer altitude. Here is without data estimation, and this one is analysis and observations, zonal wind and meridional wind. Which is that local minimum of zonal wind shift to the local noon side, which is consistent with observations. Also in meridional field, local maximum and local minimum of meridional wind shift to the afternoon side, which is also consistent with these observations. So assimilation strongly improves the horizontal wind field. Also here, the temperature field at 70 kilometer altitude in local time and latitude section. Here is freedom forecast without data estimation and analysis. And this one is LIR observations, long wave infrared observations. So the temperature field is also improved to be consistent with these observations. But the phase of summer tide differs about 6 local time. However, at the equator, compared with radio occultation observations, here is at the equator local time and altitude section, freedom forecast and analysis and observation. Which is that the phase of zonal wave number 2 component, which means semidiurnal tide, is tilted so that the local time becomes earlier with increasing altitude, which is also consistent with the radio occultation measurement. So our horizontal wind assimilation improved temperature fields also. Finally, we investigate zonal wind superrotation itself. So this one is the original one without data estimation, and this is analysis, which is that too fast superrotation is largely improved, significantly improved globally. Only assimilation at this altitude. So improvement of summer tide propagate upward or downward, then total superrotation is very similar to observation. So our data estimation is promising to produce analysis dataset. We also found the cold color hot polar vortex with cold latitudinal band is also produced in our analysis dataset. So now we submit these papers. So using data estimation technique, we also perform observing system simulation experiment using synthetic observation dataset produced by numerical models. So, for example, we now plan to cross-link radio occultation measurement proposed by NASA. And this kind of cross-link radio occultation measurement is very cheap because we need only small satellite and like GPS occultation or something. And we can observe temperature profile several points like this. And using only 1 pair or 2 pair satellite, we can reproduce hot polar vortex with cold color by temperature assimilation. So such kind of observations are promising for future missions. Also, we have tested several observations like this. Horizontal wind assimilation can produce a fast wave or not. Also, test of LIR, long infrared temperature assimilation, which can improve phase of thermal tide, and also temperature observation can modify superrotation. So here is a summary of my talk. We introduced our general circulation model and its data assimilation system. And we first produced analysis dataset using Akatsuki horizontal wind. This dataset, phase of thermal tide, is improved in horizontal wind and temperature field. Also, superrotation itself that was too fast in original AFES-Venus was successfully improved. Now, we also conduct observing system simulation experiment, which we can estimate impact of future observation and mission. So it's very promising. And our Venus fast analysis dataset we will release on the web soon. And also we plan to assimilate as another wavelength horizontal wind and temperature field. That's all. Thank you.